what we also know is that if we look at these orbital parameters here, and we think about the last, if we go back about 11,000 years ago, 11,000 years ago, what was different in terms of our orbital parameters? Eccentricity was not different. That's operating on like a 100,000 year time scale, so it's not super different. So the other options are the tilt, right? The tilt of the Earth, and that's going to vary a little bit. That's going to vary, a few percent, but that operates on a 41,000 year time scale. The other one, which operates on a 23,000 year time scale and 11,000 years, is about half that, is the wobble, right? So currently we're closest to the sun during northern hemisphere winter, closest to the sun. 11,000 years ago, the wobble would have basically allowed the orbit to sort of the wobble to do a 180, such that we would be closest to the sun during northern hemisphere summer. Okay, and if we're closer to the sun during northern hemisphere summer, that's going to do all sorts of things to climate. Okay, not only ice sheets, but also other facets of climate. So if we look at sort of summer versus winter in terms of the general circulation of the atmosphere, what sort of obvious differences do we see between a summer and winter in the northern hemisphere, for example? What sort of features do we see? Right, over the continents. So generally, low pressure over the continents, higher pressure over the oceans, and that's all due to differential heating. That's all basically like a global sea breeze. Okay, land surface heats up much faster than the ocean does. Develop low pressure over the land, rising air over the land. And if you have enough moisture with the rising air, you're going to have precipitation. So 11,000 years ago, we had more direct insolation, more direct solar radiation during our northern hemisphere in the southern our summer. Wow, I completely transposed some words there. During our summer in the northern hemisphere, we had more solar radiation, which should result in more heating, and even more so, a stronger gradient between the heating over the land versus the heating over the ocean. Okay, in that sort of situation, what you might expect is if the land heats up even more than the ocean does, you're going to have even stronger low pressure over the land and stronger high pressure over the oceans. Okay. And so in that case, what happens is that you can actually intensify the strength of the monsoons in Asia, monsoons in North America. Specifically in Asia, that's a much stronger sort of monsoonal system. Okay? And so 11,000 years ago, we had stronger summer radiation in the northern hemisphere. This graph here is kind of showing our curve of solar radiation. The black line shows kind of how it is today from a northern hemisphere perspective. And this sort of shading represents the curve of the annual solar radiation 11,000 years ago. And collectively, these two curves are the same when integrated over an entire year. Okay, but the timing of these curves is quite different, and what we see is that back 11,000 years ago, we had a much stronger sort of seasonal cycle in solar radiation. And it would actually allow for things like a stronger summer monsoon. If we had a stronger summer monsoon, what's that going to do to other aspects, maybe of climate, but maybe of vegetation? What might you expect? You had a stronger summer monsoon. More vegetation, possibly. More precipitation, absolutely. Okay, you're getting precipitation at a time of the year when you actually have the potential to actually use it. Might be good. Greater weathering, great. That's great. That's a great way to bring in the chemical weathering aspect. More precipitation, especially over the monsoon area. If you have exposed rock, you would have greater weathering, and weathering would draw down CO2 from the atmosphere. But over sort of 10,000 year, 100,000 year time scales, the weathering component, even if you increase that, it's not going to do much. It's so small. And we're talking here about a cycle that operates on 20,000 year time scale. Okay, but certainly in terms of the monsoon, dramatically modify the monsoon. Okay, and if you guys recall, I think I gave you a question earlier this semester about yes, and so you have heard about sort of this time period way back when the Sahara Desert was, lush jungle. Okay, it turned out that it was 11,000 years ago. And if that was the case, 11,000 years ago, you have more heating during summertime, more possibility for convection. And when you get convection, you can start to get precipitation. And once you get precipitation, and once you actually can start to allow for that process to continue, you can actually dramatically change vegetation types. And we can go back and look at records of lakes in sort of some of the areas in Africa, and we can actually go back and look at them through over the last several 100,000 years, and we see periods when we've seen lakes in Africa, and then the lakes dry up, but they leave behind their sort of sediments, and they very much are related to the sort of glacial interglacial cycles that we've talked about. So another record we can get at are these proxy records from caves, and so in caves, there's all sorts of interesting things going on there in terms of stalagmite formations, and these stalagmites are basically forming where we have sort of groundwater that seeps through the cave, and it combines with sort of calcium deposits, and so we get these sort of groundwater deposits that are nicely preserved in caves from other sorts of exposure, but they contain water in them, so they're containing information about falling precipitation. And when we have precipitation in water, and we're talking about paleoclimate, we're talking about looking at, again, oxygen isotopes. Okay? And it's a little different. We've talked about oxygen isotopes specifically, looking at how they vary, at high latitudes versus the oceans, and what that means about ice sheet formation, etc. Right? And here we're talking about Delta 018 records in caves, and in caves specifically in areas where we have active monsoons. So they're not necessarily going to tell us too much about sort of global ice coverage, okay, or things like that, global temperature, but they actually can be quite informative in telling us something about the ratio of evapotranspiration or evaporation to precipitation. So if you think about the sort of fractionation of precipitation, when precipitation falls, what preferentially falls out of the cloud are the heavier isotopes of oxygen, right? What evaporates are the lighter isotopes of oxygen. So if you think about it, you have stuff falling, stuff evaporating. The ratio of how those two things vary through time, evaporation is associated with, that's climatically driven. Precipitation is climatically driven. So we can actually look at these records from caves and actually infer something about the ratio of evapotranspiration to precipitation. Okay, and where we have strongly negative Delta 018 records, strongly negative. What does that mean? If it's strongly negative. If it's strongly negative, do we have more evapotranspiration or more precipitation? No. Well, let's take a look at the records. I'm going to look at two records here. One from China and one from Brazil, and they're both in areas that have active monsoons, and we'll try to make some sense of this. Okay, but one's in the northern hemisphere and one's in the southern hemisphere. Okay, so there's monsoons occurring in Asia, there's monsoons in Australia, there's some in North America and South America, but we have certainly this record here in Brazil is in the southern hemisphere, this one in China is in the northern hemisphere. Okay, so let's take a look at sort of these records from caves, from these stalagmite records in caves from both China and from Brazil. Okay, and so we have Delta 018 from caves, and we're not going to worry about the numbers here. We're going to look at the relative changes. Okay, and what we can see here is that we have Delta 018 changing, and again, the time axis here, this is for the last 160,000 years. Present is on the left-hand side. Okay, so in China, what we can see here is that when we have negative values of Delta 018 in caves specifically, that is telling us that we have quite a bit more precipitation than evaporation. Okay, and so we look at this record back through time. What we can see is that this is back 11,000 years ago, and we had sort of the the Earth being closest to the sun during northern hemisphere summer, which would intensify the strength of the monsoon, result in more precipitation, right? And we can see how this sort of varies through time. It's somewhat cyclical. There's some gaps in the record, okay? So that's in China, right? So much stronger monsoon back 10,000, 11,000 years ago. In Brazil, the opposite's true, right? So here is in Brazil. What we see here is the record actually suggests that today the sort of monsoon and sort of the Delta 018 record is stronger today than it was 11,000 years ago. So these are basically opposite in sign, which might make some sense to you, right? Currently, in the southern hemisphere, during their summer, they're closer to the sun. So that's going to invoke stronger sort of seasonality in radiation energy. It's going to invoke a stronger monsoon. Okay, 11,000 years ago, during their summer, they were further away from the sun. Therefore, they had a less of a seasonal cycle in energy, would translate into a weaker monsoon. And so this sort of record sort of is very nice because we can see sort of the opposite thing going on in China and Brazil, fairly well synced up through time, and very much related to this idea of the wobble of the Earth, wobble of the Earth's axis.